All right. What's up, everybody? Welcome back to another fun day of proof set theory and logic. Today, we're going to finish up Chapter 5, which will get us ready to start Chapter 6. That's Exam 3 material. And start talking about the real numbers. Oh boy, the real numbers. What an ungainly beast. You would think not actually that ill-behaved of a thing, right? Just numbers, but they are hairier than you might expect, right? They definitely, to the uninitiated, to people who have not thought deeply about them before, present some pathological features that you would maybe not expect. So we'll talk about that, get into that next go around. After the weekend, since remember, I sent an announcement about this last time we talked about it on Monday, no class on Friday, which is great. Halloween, right? Go have some fun, do Halloween stuff, right? Okay, cool. So last time, if you remember, where we left off was with a question. We said to ourselves, when is a function f from a set x to a set y invertible? And we already know the answer to this, so this is in some ways a silly question, right? I mean, what's the answer, right? When it's surjective and injective, right? Okay, we've already seen this, but actually going through and verifying it is sort of the focus of this, getting used to the more rigorous formalism of it all and not just accepting that as some sort of a given. Since after all, while our blob-type diagrams inform our intuition well, perhaps they break down if our sets are really big, like too big to draw on the board, like, have infinitely many elements and so on. There are lots of kind of pathological behaviors you can encounter with larger sets, right? Here's kind of a good example of this. It's a classic one, just really quickly to, help you think about why it is important to actually go through and definitively show this. So what if you had I'm going to do a terrible job of just throwing this classic thought problem out. But what if you had but we'll talk about this actually, maybe I'll bring this up again when we talk about cardinality soon. But what if you had a hotel with one room for every one of the natural numbers, and it's full up, right? Someone shows up and they say, I want a room. Do you tell them you gotta leave? Or can you find some way to give them a room? What do you think? Yeah, just put them in the first room and tell everyone to move down a room. Does that seem right? Maybe it seems a little bit weird since you said the hotel's full and somehow you put yet another person in there. But if you think about it, if this was somehow impossible to put one more person in there, well, then someone would end up without a room. So you should be able to tell me which person doesn't have a room. Which one would it be? You can't come up with one, right? Because every person just went to the next room over. Yeah. So if you say, who doesn't have a room? Is it that guy? I'd be like, no, he just went to the next room over, right? The fact that there's, endlessly many rooms is the thing that kind of takes care of the potential problem there, right? So maybe you can run into some kind of weird behavior when you're mapping large sets to other larger sets, right? And the natural numbers, they aren't even that big. There's far larger sets. So maybe there's crazy stuff that goes on. Hence, we should not just purely rely on our intuition about these blobbish diagrams, right? We need actual formal reasoning. So here is the first theorem we will show. Perhaps obvious. If f is a function from a set x to a set y that is invertible, then f is injective. Or thinking of it from the contrapositive, not injective implies not invertible. Yeah? Okay. Quick sidebar really quick. Does everyone remember our convention regarding invertibility? Okay, if you don't, our convention is that if you have a function f, so here, quick, convention, we say a function f is, is invertible if its inverse the set of yx's such that xy is in f, an ordered pair there, is itself a function. So under our convention, we were like, hey, every function has an inverse in the sense that you could just flip all the ordered pairs. It's just the case that many functions have inverses which are not themselves functions, but instead, far less well-structured relations. Okay, so we're starting off by assuming that our function is invertible. That is, if you flip the ordered pairs, you still have a function. Our claim is that it is injective. Let's prove it. All right, what would you start with? Actual question.
Suppose that it's not injective.
Okay, you want to go for that way. Go say, suppose it's not injective, and then show it's not invertible. This is a pretty reasonable thing to do. Sure. Okay. So I'll say, we prove the contrapositive. Since, after all, the contrapositive is logically equivalent to the original implication. To that end, suppose f is not injective. Okay. By definition, this requires that there exist x1 and x2 in X with x1 not equal to x2 such that f of x1 is indeed equal to f of x2. Yeah? Hence, x1, f of x1, and x2, f of x2 are both elements of f. Since remember, a function is just a set of ordered pairs. Yeah? Our notation of f of x equals y, this like machinery type of thing where you put in an x and you get out a y or something, is just shorthand to denote the inclusion of the ordered pair xy in f. Okay, so both of these are elements of f. Therefore, f of x1, x1, and f of x2, x2 are elements of the inverse of f. But f of x1 equals f of x2. So this says that there exists y in big Y such that yx1, yx2 are both in the inverse of f with x1 not equal to x2. Hence, the inverse is not a function. After all, the condition to be a function, remember, is that if AB and AC are in, I don't want to use F again, but I will. I'll say in G, if G is a function, right? Then this must imply that B is equal to C. That's part of the definition of a function, right? So you need two things. One thing says that there is no ambiguity what an input is mapped to, right? It's not the case that an input is mapped to two separate outputs. Each input has a unique output. Well, I want to be clear there. It's not the case that the output of an input is the only thing that gets that output. But there is no input with two outputs, right? That's what I mean by a unique output in that sense. And then there's another piece you also need, which says that for all elements of the domain, there exists an ordered pair in G with that element as its first entry. These are the two conditions that you need for a relation G to be a function. It maps everything in the domain to something, and nothing in the domain gets mapped to two different things. Everything's got an arrow going out of it. Nothing has two arrows going out of it. Yeah? Okay, so functions. We've just shown that the inverse relation is not a function. Since these two things are equal, it's saying that it maps the same thing to two different things, violating the first one of these bullet points, right? Okay, cool. And so invertible functions are injective, have to be. What about surjectivity? Should we do that one next? Let's do it. Why not? Okay. All right. Though perhaps actually, let's take a slight diversion very quickly before we do it. Forgot I put this example in here. Quickly, let us define f from the naturals to the naturals by f of n is equal to n plus 1. It takes a natural number and it gives the next one. It's like the successor of it, yeah? Okay, cool. Is this function injective? What do you think? It is. It is. Yes. If f of n equals f of m, then n plus 1 is equal to m plus 1. And by subtracting 1 from both sides of this equality, Butterfingers, n is indeed equal to m. Yeah? Subtract 1 from both sides, n is equal to m. Okay. So that's injective. Is it invertible? What do you think? No, and why not?
At value 1 domain value.
To see this, it is not. let's consider the inverse. Let's call it G. That is, G is just the set of ordered pairs n plus 1, n, such that n is in the naturals, right? Were this to be a function from n to n, we require, well, the two things we just had up there. First, we require that no input gets mapped to two different things, right? Nothing has two arrows going out of it. We also require that everything has one arrow going out of it. We require that each, I'll write it this way, n in n have at least one ordered pair in G such that it is the first entry. Okay, so you need everything to have at least one ordered pair with it as the first entry. That is, oh, is my camera control broke? There we go. That is, if G is a function, then for all n in the naturals, there must exist, I would say, I'll put it another way, m in the naturals, such that n m is in G. That is, this quantified predicate, this proposition, must hold. But consider the natural number, say 1. Remember, under our convention that we're doing in this class, 0 is not a natural. So 1's the first natural number. We start counting at 1. Yeah? So consider the natural number 1. If there exists m in n such that 1m is in G, we have that m plus 1 equals 1, i.e., m equals 0. But 0 is not in the naturals. So there is no such ordered pair. That is, this fails to be a function. Therefore, G is not a function, and F, while injective, is not invertible. Yeah? Okay. So notice, invertibility requires injectivity via, when we wrote the definition up there just a minute ago, via that first condition, right? That nothing has two arrows pointing out of it. But that's not enough. There are two conditions to be a function. It's not enough just to have nothing with 2 arrows pointing out of it. Everything must have at least 1 arrow pointing out of it. Yeah? Okay, so can you imagine what criteria gives us that? Surjectivity, right? Okay, so let's do it. Theorem. If f is a function from a set x to a set y that is invertible, then f is surjective. Okay. So a function from a set x to a set y that's invertible has to be surjective. Proof? How would you go about doing this? Would you perhaps do the same kind of trick as before? Prove the contrapositive? Let's do it. Okay. We prove the contrapositive. To that end, suppose f is not surjective. Okay, what does it mean to be not surjective? Right on. Okay, so then there exists y in big Y such that f of x is not equal to y for all x in big X. Yeah? Okay. Hence, there is no element yx in the inverse of x. Or I'll even write it this way. There's no element AB in the inverse of, not of x, of f with a equal to y. Or maybe I won't even say it this way. This is going to be pedantic. I'll say there's no element yx in the inverse of f. And correspondingly, the inverse is not a function from y to x. Hey, there we go. Perhaps said kind of pithy, but we've really hammered this point home a lot. Yeah? That is, there is some y in y such that yx is not in there for any x. Maybe I should even say that to be extra clear. In the inverse of f for any x, and correspondingly, the inverse is not a function from y to x. That is, there is no ordered pair in the inverse with that y as its first coordinate. That is, there are things in y that don't get mapped to anything in x by the inverse. Cool? All right. Nice. Putting these things together, we get the following theorem. Okay. A function f from a set x to a set y is invertible if and only if it is injective and surjective. That is, these are equivalent statements. Injectivity plus surjectivity is the same thing as invertibility. Tight. Okay, great. That's exactly what we hoped to show, right from the get-go. Okay, so one direction is easy. in the forward direction, suppose f is invertible. Then, by the last two results, f is both injective and surjective. That is, we just showed that if f is invertible, it's surjective. And then on the other board, we showed that if f is invertible, f is injective. So we get that side for free, right? That's a super easy part. Now let's go the other direction. In the reverse direction, suppose f is surjective and injective. Yeah? We'll show that its inverse is indeed a function. Okay. Let's write G to denote the set of y(x)'s such that f, or I'll write it this way. I'll write it as, I'll say y(x)'s such that xy is in f. Okay. Now, for this to be a function, we show g is a function. That's what we're going to do. For this to be a function, every y and y has to appear as the first element of some ordered pair. And indeed, every y and y must appear as the first element of but one ordered pair. Okay, so to wit, I'm going to get kind of low on this board. Perhaps I should go over to another board. We'll see if we have enough room. To wit, observe that surjectivity yields that for any y in y, there exists x in x such that f of x equals y. So, for all y in y, there exists, I'll say x in x, such that yx is in G. Do you agree with that? After all, writing f of x equals y right here could be equivalently represented as xy is in f. Yeah? Putting it perhaps onto the next board in an easier to read location. Let me write this more succinctly. Is that how you used to spell succinctly? Probably not. I don't know how to spell succinctly. My shame is known. I don't know how to spell succinctly. Okay. Surjectivity of f yields that for all y in y, there exists x in x such that xy is in f. This yields via the definition of G that for all y in big Y, there exists x in x such that yx is in G. That's that first condition we need to get a function, yeah? All we're doing, I'm writing it out very straightforwardly right here to say, look, same exact thing except that I switched this around and I wrote a G instead of an F. But G is just defined as, like the flipped pairs that are in F. So, hey, there you go. That's all it is. Okay, now let's show that we have the other condition we need for a function. Okay. By the injectivity of F, F of, I'll even write it this way, for all x1 in x, for all x2 in x, f of x1 equals f of x2 implies x1 is equal to x2. That's the predicate. This is the quantifiers for it. Yeah? Writing it out formally looks hairier, but hey, just to be very clear, this is what injectivity says. It says that if you have any two elements with f plugging those elements in equal, right? Any two elements that get mapped to the same thing, then those things are equal. Yeah? Okay, cool enough. Cool enough. Now, so how do we get the last condition we need to show that G is a function from this? What do you do? What do we even need to show, to be clear? We need to show, we've shown that everything has at least one arrow pointing out of it. Now we need to show that nothing has more than one. Yeah? So, having yx1 and yx2 in G implies x1 is equal to x2. Yeah? Does that make sense? What we just said, we said, hey, we want to make sure nothing has two arrows pointing out of it. That would be something like there's a y here, there's two different x's here, and it points to both of them. Well, you can fix this by having those actually be the same exact thing, right? That's what you really need to show, is that there's never a case where you have one thing pointing at two separate things. Yeah? Okay, hence, G is indeed a function from y to x, and f is therefore invertible. Does that seem reasonable to you? Feeling good about this? I feel like some ways through this, people are giving me some looks that are like, I don't like this at all. But maybe it's that I wrote the actual quantifiers, like in like the full predicates. It looks worse. If you don't like writing the full predicates, you can say this without them, right? That is, if you don't like writing all the full predicates, you could say something like, by the injectivity of f, for all x1 and x2 in x, if f of x1 equals f of x2, then x1 equals x2, right? It's a lot more words, but if you like writing it that way, that's perfectly fine. It's just shorthand for the same thing. I mean, the other way is shorthand to say this, right? It's not like the symbols give you any sort of like magically make your proof more correct or something like that. You can just say it in plain English if you prefer. It's saying exactly the same thing. It is more compact to write it the other way, so perhaps that makes it a little bit easier to see. At least it makes it easier to see, I think, that, like for instance here, with the first requirement that everything gets mapped to something. I think it's much easier to see by writing out the quantified version of the predicate here, because it shows that the only thing I'm doing is I'm switching the order and turning my f into a g, right? Maybe it's easier, I don't know, depends what you prefer. But how about that? Okay, now we know that functions are invertible if and only if they are both injective and surjective. It's the same condition. Cool. There's something that we didn't end up touching back on yet, which we talked about at the very beginning. That is, we've said, hey, when do you have an inverse function? When can you flip everything and still get a function? But this is actually kind of a strong property, as we can see, right? To get an actual inverse, we need both injectivity and surjectivity. It's not enough just to have one. So what do you get if you just have one? Do you just get nothing? Do you just get, well, whatever that thing is? Like you just get injectivity or you just get surjectivity and it has nothing at all to do with inverses unless you've got both of them? No. There is a good answer. So as kind of a little bit of bonus math for us, let's look at what you actually end up getting. So question, what if you only have one? Make sure, oh, I did switch the camera, good. And I've written on a slightly wet board, so I've probably doomed that marker. Oh no. Let's see. That is, what if f from x to y is injective, but not surjective, or surjective, but not injective? Clearly, f is not invertible, but do we get something similar? That's a terrible marker now. And also not that good. Squeaky marker. Do we get something similar but weaker? Okay, here's the setup to kind of put this in your head of what's going to go on here. So suppose we've got our set x, we've got our set y, and then we just duplicate our set x. Now, usually, if we have an inverse, we would expect to be able to take y back to x just by flipping the arrows around, right? The usual picture of inversion is like you've got like 1, 2, 3, you've got like A, B, C, you know, somehow f maps things around. And all you have to do is basically take this and flip it and duplicate it, right? Like turn it over this plane, right? You kind of see what I'm saying? Like you can imagine if you could just pick this up off the board and like turn it around, right? It would tell you what the arrows should be for the inverse. Okay, well you could ask the same question about, hey, when can I get back to where I started? And the answer turns out to be different than requiring full invertibility, requiring full injectivity and surjectivity. That is, when you have an invertible function like this, it's super easy to say, how do I get back to where I started from here? Well, I went from 3 to a, and I want to go back to 3. Boop, 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 back to where I started, right? I went from 1 to b, and I want to go back to 1. Boop, back to where I started. I went from 2 to c, and I want to go back to 2, back to where I started. And you can see exactly what I'm saying here, hopefully, about like flipping this over, right? They're like mirror images of each other, yeah? Okay, what if we have, say, for instance, a D right here? I could map D to whatever the heck I feel like, and I still get back to where I started, right? I only needed injectivity to be able to do this. That is, if I had, for instance, 3 pointing at, instead of A, if I instead had 3 pointing at, I don't know, pick anything else, like say B, yeah? Then I wouldn't know whether B should get taken to 1 or to 3. Or to put it another way, if I pick 1, then 3 gets taken to the wrong place. I don't end up back where I started. If I follow 1, I do end up back where I started, but 3 is now not back where I started, right? Okay, so if I have injectivity, then I have a function that I can do afterwards and get back to where I started. So injectivity by itself is enough to find a function that I can do afterwards to get back to where I started. At least in this case, we should show this formally. That is, here's the claim. Injectivity implies there exists a function g from y to x such that g of f of x equals x for all x in x. I can put a function to the left of my function and get back to where I started. Can I do the other thing? Can I put it on the right? That is, if I say the other one here, say there exists a function g from y to x such that f of g of y is equal to y for all y in big Y, some function I can put inside of f, some function I can do first instead of after to get back to where I started in y. Yeah? It's the same picture, but now instead of putting something afterwards, I just have another copy of y beforehand with like A, B, C, and here now D. But look, now I have some trouble. That is, if I want to just follow along here and get back to where I started in y, right? If I do the same process, but I skip the end step, and like don't look at this x over here, and say, okay, well, I'll take A to something, and I want that something to be something that gets sent back to A. Yeah? I can do that, A to 3 to A. B, well, what should I take it to? I should take it to something that gets sent to B. Yeah? Okay, here's something that gets sent to B. C, I should take it to something that gets sent to C. Here's something that gets sent to C. D, I should take it to something that gets sent to D. Nothing gets sent to D. Oh no, right? Notice, this means that I need surjectivity. I need everything to get hit, right? Otherwise, there's stuff that I can't follow over to get back to it because there's no path to it in the first place, right? Okay, but notice I don't need injectivity. That is, if instead now perhaps I get rid of this D just to make our lives easier, and I make this like 1, 2, 3, 4, and 4 maybe gets sent to C, there's nothing that's stopping me from doing this process still. If I follow C, I get over to 2, and I get back to C. If I follow B, I get over to 1, and then I get back to B. I follow A, I get over to 3, I get back to A. So I've lost injectivity, and I'm all good. That is, surjectivity implies the existence of a right inverse, a function you can put inside the function to get there. So it's not the case that injectivity and surjectivity magically combine to give you invertibility, but by themselves they tell you nothing. It's just that an inverse, in the way we usually think of it, is a two-sided inverse. It's both a left and a right inverse. Injectivity by itself is enough for a left inverse, while surjectivity by itself is enough for a right inverse. Naturally, if you have both a left and a right inverse, you have a genuine inverse. That is, we could have gone through this by showing that injectivity implies a left inverse, surjectivity implies a right inverse, and then showing that when you have both a left and a right inverse, they are the same. Yeah? So, kind of a fun thing to think about if you're ever like, oh, I can't invert this function. Like, you know, if you're like coding something or in some way dealing with it, a lot of times people will go like, oh, this function's not invertible, I can't say anything. But if it's surjective, it's right invertible. And if it's injective, it's left invertible. And most of the time, a lot of the time at least, this is enough to answer your problem. So, all right, cool, whatever. Great. I'll see you next week. Have a great Halloween. Happy Halloween.